Okay, guys, Mr. Block, this is the Unit 8 study guide, and I'm just trying to go over it real quick. I'm going to make sure that this video stays within 15 minutes because that's the longest that the screen capture will let me do it. So we need to know our symbols. And the battery, the one thing that I want you to see is this battery is pointed this way with the plus here, so my plus is this way. And this battery is pointed down, so my plus is this way. Okay, this is the bulb, the switch, and these are the resistors. Okay. This is pretty self-explanatory. And so we have to get to here. And so these are some questions that you need to know. And I put them in series and then parallel on the second page. And so we ask ourselves all the time, you guys have been practicing this for a long time. If something happens to something, what happens to something else? And we've been doing this all year. And so we always say we either know the science or we know the math or we know both. And if our theory or our answer matches with both the science and the math, we're good. All right, so the first one talks about if the battery is up, if we add voltage to the battery. Well, science tells us that if we add voltage, then we should be adding more energy, and so current must be going higher, okay? And so the science tells us the current's going to go higher. But we can look at Ohm's law, V equals I times R. If we make this number V go up, then one of these two numbers has to go up, and so current will go up. Okay, so that's why our idea goes, our science and our math match. All right, the second one asks about the resistor in series. If we take another resistor and make it larger. Well, the science tells us that if we're a resistor, we kind of like we're squeezing the pipe. And so if we squeeze the pipe of an electricity, we're going to make it harder for the current to go through. And so the current must be going down if we make a bigger resistor. And if we look at the math, this makes sense because if we don't change the voltage, but we increase the resistance, then this number I must go down to keep this number the same. Okay, and so now our science and our math, they match. If you take a resistor out of the circuit and you just don't put it back in, well, now you've left the circuit open. Current can't go around in a series circuit because it hits a spot where there's no connection, and so the current will go down to zero. All right, and the last thing was, in a series circuits, what's the connection between the voltage of the battery and the voltage drops? We kind of talked about that in one of the other things, but basically we need to remember that if we are thinking about electricity correctly, if we're in a little electron, we're going to be racing around this circuit. And when we get here, we're dead tired. We have no energy. The battery is going to give us energy, and then we're going to have to lose it all on the way through to get to the back of the battery again when we're zero again. And then we gain energy, and then we lose it. And then we gain it in the battery, and then we lose it. Why do we lose it? Well, we change it into light or change it into heat. And so the connection between them is Kirchhoff's law, and that is the voltage of the battery has to equal all the voltage drops. Okay. Now, we've got the parallel. And so the parallel one that says if the battery of the parallel goes up, well, if we add more power, doesn't matter if we're in parallel or if we're in series. If we add more power, the current is coming out of the battery is going to get bigger, so the current's going to go up, same as series. It says if you add a resistor in parallel, and so what we always say is that when we add something in parallel, we add another spot, another bunch of pipes for the current to go through. So if we add another set of pipes, it's going to be a lot easier for the current to go through. I always think about it this way. If you got cars all stacked up in a row in one lane, and then you come to a spot where then it goes to 3 lanes, well, then all of a sudden one car can go this way, one car goes this way, one car goes this way. All of a sudden traffic opens up. Same thing with current. If we give them more paths, more current can get through. And so if we add a resistor in parallel, the resistance is going to go down, and so the current's going to go up. All right. If we take a resistor out and leave it open, do you see how these have independent paths here, right? In a a parallel circuit. So if we break the circuit here, there's still a complete path for this one to work. And so that's the great thing about parallel, kind of like in Christmas lights. You step on one Christmas light. If it's in series, then the whole thing goes dead, right? Because there's a break in the circuit. But if we wire all of those lights in parallel, and we step on one light and the rest of them stay on because, right, even if we break this bulb right here, this one's still going to keep going. All right. So it says the rest of the circuit will continue to run. And then for parallel circuits, what's the connection between voltage of the battery and the voltage drops? Well, here, now each loop is independent. And so if we gain, let's say 6 volts here, we have to lose 6 volts here. And if we gain 6 volts and we go around the outside, we have to lose 6 volts there. Okay. All right. We're at some of the easy problems. We all need to be able to get these problems right. So if we have problems that just have Ohm's law, I'll write down both V equals I times R and I equals V divided by R. Make sure you use whichever one you're more comfortable with. We use this one so that we don't make a mistake when we're rearranging. Okay. Conductors and insulators. Conductors allow for electricity. Insulators stop it. And then here we start our problems. Okay. And you guys, we're going to go over this. I'm going to come talk to you guys on Tuesday before the test. And so we need to learn how to do these in steps. Series is pretty simple. We're going to do step 1, step 2, step 3. Step 1, add them all together. Boom, we add them all together. Step 2, we redraw. Step 3, we write down Ohm's law and we find the total current. Right? Once we do these 3 steps to get this done, then we say to ourselves, all right, this is the current. And so if the current is 0.25, well, then it's got to be the same everywhere, here, here, and here. So I can put them all there, right? And then I can multiply across, because V equals I times R. And so we can multiply across, and the check is, if these all add up to the battery, we've done it right. Because why? If we gain voltage here, we have to lose all that voltage there. Okay, so if we gain 4.5, we have to lose 4.5. And so if we add these 3 numbers up, we get 4.5. Right, that's a series circuit. A parallel circuit is a little bit different, but we're going to try our best to use the same steps. So the step 1 was find the total resistance, but we have to use the different equation. So step 1, same as series, find the total resistance, but use 1 over RP equals 1 over all of the resistors. Take your time, find the common denominator, add them up, 5/9, and then flip them. 1 over RP, RP over 1. We get 1.8. Okay, so step 1, step 2, redraw. Well, now we have a 4.5 volt battery and we have a 1.8 resistance, right? And so we can write down V equals I times R and find the total current. So if we were to draw that total current in right there, right, what have we found? Well, we really have found very little, because now we know that some of it goes this way, some of it goes this way, some of it goes this way. We don't know how much here. So we cannot write anything down here. And if you do, you're going to make a mistake. So once we get to a trouble spot and we say, okay, we ran out of information with our current, now we have to go to voltages. And so what we learned is that if we gained 4.5 volts here, well, then we have to lose 4.5 volts in this middle, or this little tiny circle right here. So we can write down 4.5 here. If we're a different electron, if we gain 4.5 here, we're going to lose 4.5 across the 9, or the 3. We're going to lose 4.5 across there, so we can write it there. And if we gain 4.5 here and we take the outer loop, we're going to have to lose 4.5. So we can write all of these as 4.5. And now we can use V equals I times R to find what the current is. So 4.5 divided by 9 is 0.5. 4.5 divided by 3 is 1.5. 4.5 divided by 9 is 1.5. Now, why are we adding these up? Well, because we said 2.5 was going to come here. And now we just found out that 0.5 goes this way, 1.5 goes through the 3, and 0.5 goes through the 9. And so if we add up 0.5, 1.5, and 0.5, we get 2.5. We get the answer. Right? We got to be able to understand that. And so you guys are constantly looking for shortcuts. You're constantly looking for some sort of pattern. That's what we taught you in kindergarten, to look for patterns. Now is the time to learn the science. And the science behind circuits is we find the currents, and we know that the currents have to add up in the branches, and we know the voltages have to follow the voltage rule. And that's the science. Okay, if you want to keep playing the game of trying to figure things out in kindergarten, then we're going to be in trouble because we're ninth or 10th graders now. All right. Now, I'm not going to go too long in this one because I want to get this all in one video. If you're at combination circuits, you can see what I do is I start with step 1. I put these two together. I redraw. That's step 2. I realize that when I redraw that I don't have a simple circuit. So then I start again with step 1. I find the total and I redraw. Okay. And then once I know that I have a simple circuit, I can find the current. And that's when we have to keep going back and forth. We know the current, the total current, we know the total resistance, right? And then we have to say to ourselves, okay, if I know the current here, I can find the voltage drop here, here, and here, right? I can put those down and I can find the total voltage drops. And then I have to start playing with voltages. And so I will talk to you guys a little bit more about that when we're preparing. All right. This thing right here, it says the student is creating a circuit that contains identical light bulbs. Which ones are going to be the brightest? Well, the parallel ones are going to be the brightest because if we have a 9-volt battery, then if we put them in series, then this is going to lose 3 here, 3 here, and 3 here. And so those are going to lose 3. That's the energy that they're losing is 3. But if we put them in parallel, it's going to gain 9, and it's going to go here, it's going to lose 9. If it goes through the middle one, it's going to gain 9, it's going to lose 9. And the outer one, it's going to gain 9, it's going to lose 9. And so each one of these bulbs is going to burn at 9 volts. And 9 volts means more energy, means more brightness. Okay? All right. I think this is the last page, so good for us. We're going to stay there. So here are our symbols. Make sure you know them. These are the power equations. Power equals I times V. So we can either tell you to find power or we can find one of the other ones. So we can find current. And then here's a problem that we did a couple times in the worksheet and once on the quiz. We give you the power of something. We ask you to convert it to kilowatts, right? And so that's just divide by 1,000. Then we say, all right, now take that power and multiply it by however long we use it. So in this instance, we use it for half an hour. So we multiply this number times the time we use it. Now we have it in kilowatt hours, right? Because kilowatts times hours gives us kilowatt hours. And lastly, we ask you how much does it cost? And if you have been following us when we talk about conversions, we write down what we have. So we write down this number. We build a conversion factor. And the problem tells us that it costs us 18 cents for every 1 kilowatt hour. So we just multiply this times 18 to get the power or the amount of money that we're going to spend. Okay, I hope I didn't skip I don't think I did. So like I said, I'm going to come talk to you guys on Monday and a little bit of discussion, but we'll figure out what's happening on Tuesday, tomorrow morning on Monday. Okay, so let me just tell you that my goal right now is that you guys in Moises' class are going to have your test on block day. And then I'm going to spend Tuesday with you guys talking about these things. Talk to you soon. Bye-bye.